And hello to all dear students. Do you have my voice? In the previous session, we see this definition. Let me read this definition again for you. Let G be a locally compact group and let E be a subspace of L infinity containing the constant function and closed under complex conjugation. Okay. Then E is left invariant if for all phi in E and for all G in all group delta G star G belong to E. Then we say that E is a left invariant subspace of L infinity. And if E is left invariant subspace of E, then a mean such as M on E is called left invariant if we have this equality delta G star M of delta G star phi equal to M of phi. Then we say that M is a mean or left invariant mean on E. M is a left invariant mean on E. And finally, we see this definition: a locally compact group G is amenable if there is a left invariant mean on L infinity of G. If we have a left invariant mean on whole of L infinity, okay? This is the definition of left invariant mean on E, on a subspace of L infinity. If we have M left invariant mean on whole of L infinity, then we say that G is an amenable group. Okay? And for example, I say that three groups with two generated is not amenable. You can see the proof of this in chapter 0. Okay? But the second example is for compact group. Let G be a compact group. So L infinity is L1. Okay? Let me write this for you. Please note that if G be a compact group, let me add another slide. Please note that if G is a compact group, then mu of G is finite. We consider Mg. mg of g is finite. Okay, and also in this case, if G is a compact group, we have L infinity is a subset of L1 because if, for example, F considered as an element of L infinity, then the infinity norm of F must be finite. Okay, this is a real number, a positive real number. And the absolute value of F is less than or equal the infinity norm almost everywhere. Okay, we know that because this is the supremum norm of this. Okay, so the integral of absolute value of F with respect to this Haar measure on G is less than or equal the integral of this norm d mg on G. Okay, because this function is less than this function, and this is equal to this norm because this is a real number. Okay, multiplied by this integral dmg, and you know that this is equal to mg of g, so that this is equal to this norm multiplied by mg of g, and this is a real number and this is a real number, so that this is a finite real number. This integral is finite, therefore F must be belong to L1 of G, so that for any F, please note that we consider this F as an element of L infinity, and we see that this F must be belong to L1. Consequently, any element of L infinity is an element of L1, and you prove this inclusion. Okay, we have this inclusion. Let G be a compact group, so L infinity is a subset of L1. Let mg denote normalized left Haar measure on G, and define this. Normalized means this. Mg divided by mg of G. Okay, if we consider this as mu, then mu of g equal to 1. We say that this a normalized measure. In this book denoted this mg of g denoted by mg itself. Okay, let mg denote normalized left hand measure on g, and define this functional on L infinity. M of phi equal to this integral, and we know that this integral is finite. This is the real numbers. Okay, by this statement, any element of L infinity is an integrable function. Okay, is an integrable function. So we define mu from L infinity to complex number, for example, by this function rules for any f in L infinity of g mu or m, for example. Let me write similar of book m of m of f equal to this integral f dmg. Okay, this is the real numbers, because, or complex numbers, because this must be finite. Okay, this must be finite, because we see that L infinity is a subset of L1, so that this integral is finite, and this is an integrable function. Now it is very trivial that this function is bounded. M of alpha f1 plus f2 equal to alpha m of f1 plus m of f2 and also the norm of this function equal to, this is supremum norm. Okay, this supremum of m of f such that norm infinity of f is less than or equal 1, and this is trivially equal to 1, and also m of 1 equal to 1, because m of 1 equal to this integral. Okay, 1 dm, and this is mg of g, and this is equal to 1 because we consider normalized Haar measure. So this example is very trivial, that this m by this function rows is a linear bounded functional on L infinity, and also this is a left invariant mean. I think I write this also for you. Yes, the norm of m equal to 1 and equal to this, because the norm of m equal to this supremum, and this is less than 1, and m of 1 equal to 1. So we have these two equalities. So m is a mean on L infinity. Moreover, this mean is left invariant, because for each f in L infinity and for each g in g, m of f star delta g equal to m of lg of f, and this is equal to this integral lg of f, not f, mg of x, mg of x. Okay, this integral takes for x as variable, but this equal to this because m is left invariant. This integral with this integral are equal, and this is equal to m of f. So we have a left invariant mean on whole of L infinity, so that G is an amenable group. So G is amenable because we found a left invariant mean on L infinity of G. Any abelian groups is an amenable group, and we can see the proof of this in example C. And I omit the proof of this for you because you must see some references, but this is very important that you know any locally compact abelian group is an amenable group. And we have this definition. Dear students, do you have my voice? Let G be a locally compact group. P of G equal to the set of all integrable function such that f is non-negative and one norm of f equal to 1. And let E be one of the following spaces: L infinity, CB, LUC of G, RUC of G, and UC of F star delta equal to M of phi. Then we say that M is a topologically left invariant. Topologically left invariant mean. It is very trivial that P of G is a subsemic group of L1 with convolution, and we have this exercise show that a topologically invariant mean is the sense of definition above is well defined. Equivalently, if E is any of these spaces and if phi belong to E and F belong to P of G, then F star G must be belong to E again. Okay, please solve this exercise as an homework. This is not difficult for you, and we have this lemma. Let G be a locally compact group and E be any of these spaces, then every topologically left invariant mean on E is a left invariant mean. Every topologically left invariant mean is left invariant mean. Okay. Let M in E star be a topologically left invariant mean. We want to prove that this is a left invariant mean too. Okay. For this, let phi belong to E and G belong to G. Fix a function f in P of G. Then we have these equalities. M of delta G star phi equal to M of F star delta G star G, because M is a topologically left invariant mean. Okay, topologically left invariant mean, so that for any element of P of G we have this equality. Okay, now this is an element of P of G, so that this equal to this M of phi, M of this function of P of G star phi. Finally, we see that M of phi equal to M of delta G star phi, and this is the definition of left invariant mean, so that M is a left invariant mean. And I write this again for you. M of delta G star phi equal E and equal to this term. This is the proof for this statement. F star delta G is an element of P of G. I recall that P of G equal to the set of all integrable functions such that this is positive and this norm equal to 1. Okay, this norm equal to 1, because this is the norm 1 of this function f star delta G. Okay, equal to this integral, and this is equal to this, because f star delta G equal to this internal integral. This integral is this function, okay, f star delta g. And by the Fubini's theorem we can replace the order of these two integral, okay, this repeated integral and this equal to this is modular function, and the integral with respect to this point mass measure equal to this. You must take instead of t g, okay, so that is equal to this is okay x y inverse, this is t inverse, okay, this must be t inverse, okay, delta of the inverse of t. So you must put instead of t g, x g inverse delta g inverse, and we must take this integral with respect to this measure, and this is equal to the integral of f with respect to this, and this is equal to this because f is a positive function. The absolute value of f equal to f, and this is equal to the one norm of f, and this is equal to 1. This is equal to 1 because f considered in p of g, so that this norm is equal to 1, okay. And so if f belong to p of g, f star delta g belong to p of g again. Demo, let G be a locally compact group and M belong to the dual of uniformly continuous function on G. This M be a left invariant mean, then M is a topologically left invariant mean. Topologically left invariant mean. And its proof is straightforward. Okay. This is a very nice lemma, and the proof is straightforward. Let me read again this lemma. Let G be a locally compact group and let M be in the dual of UC of G, and M be a left invariant mean. Then M is a topologically left invariant mean. so that any left invariant mean on this space is a topologically left invariant mean. And in the previous lemma we see that any topologically left invariant mean on L infinity is a left invariant mean. Prove let phi belong to UC of G and F belong to L1 of G. Since M is left invariant, we obtain this equality because M is left invariant, so you can omit this delta G. Okay, for each phi in UC of G, this functional F maps to M of F star phi F belong to L1 is continuous, so that there is a function psi in L infinity such that we have this equality. You know that the dual of L1, this is hold for this reason. Please pay attention. You know that the dual of L1 of G star equal to L infinity of G, so that for any functional such as T in L1 star, this T must be belong to L1, must be belong to L infinity. Okay, and this equality holds by this homomorphism. For any, for example, F in L infinity, if we define TF, for example, from L1 to C by this function rules, for any H in L1, TF of H equal to this integral F H d M. Okay, on whole of T. It is very trivial that this TF is a functional on L1. Okay, so that any function in L infinity make a functional on L1, and we have this result that the map from L infinity to the dual of L1 by this function rules is an isomorphism. Okay, isomorphism. So any element in the dual of L1 must be TF for one F in L infinity. As a consequence, if we, for example, denoted this by H, this H is onto, okay? H is onto, so for each T, for example, in L1 star, there is a function f in L infinity such that T equal to TF or equivalently for any F in L1, T of F, or for any H, because we use F for any H, okay? T of H equal to TF of H, and we know that this is equal to this integral, okay? So that since this function such as T is continuous and bounded, is an element of L1G star, there exists a psi in L infinity such that we have M of F star T. This is, for example, or function in the dual of L1. This must be equal to this. From this, it follows that psi equal to delta G star psi for all G. So psi is in fact a constant, and this is very trivial that if we have this for all, this F must be a constant function. So that 1 is function, okay? Yes, students, please. This is very easy, but please prove this. If we have this, then F is a constant function, okay? Please prove this as an exercise. This is easy. So for any phi, there is a constant in C such that we have this equality. For each F, it follows that this is equal to C of P by theorem. This is in our appendix A that we review some of context in this appendix. There is a bounded approximate identity for L1 containing in P of T. So this net is bounded left approximate identity for left one of L1 module UC of T, and for each F in P of T and phi in UC of T, we have these equalities. M of F star G equal to M of this, because this limit equal to this, and this is equal to C of P, and this is equal to this limit, and this limit equal to this again, because this limit tend to phi, and and M is continuous. Finally, we see that M of phi equal to M of f star phi. So M is a topologically left invariant mean. Existence, let G be a locally compact group for each of the following subspace of L infinity. Does the proof of lemma 118 still work for all of this? Okay, you can prove this by a similar method of this lemma. And finally we have this very important theorem. For a locally compact group G, the following are equivalent. G is amenable. You know that G is amenable equal to is equal to there is a left invariant mean on whole of L infinity. Okay, G is amenable equal to this. Now by this theorem there is a left invariant mean on not off. Okay, existence of a left invariant mean on L infinity of G equal to existence of left invariant mean on CB of G, and this is equal to there is a left invariant mean on LUC of G, and this is equal to there is a left invariant mean on RUC of G, and this is equal to existence of a left invariant mean on UC of G. Okay, and it is a very important theorem, and its proof is easy because, for example, 5 implies 1 must be proved. Other implication is easy. For example, if we have a left invariant mean on whole of L infinity, we can consider the restriction of this on CB of G. Okay, the restriction of this on CB of G. This is the left invariant mean on CB of G, and then the restriction of this on LUC of G, because this is the subset of CB of G. And also if we have a left invariant mean on RUC of G, we can consider the restriction of this on UC of G. We found a left invariant mean on UC of G, and we say the proof of 3, 4, 4, so that only we have for this proof. Okay, other situation is easy. This is the theorem. G is amenable if and only if there is a left invariant mean on L infinity. This is the definition of amenability. Is equal to there is a left invariant mean on CB of G and other spaces. So it's proof. We see that, for example, from 1 to 2. I say this for you. Since G is amenable, there exists an element such as M in the dual of L infinity such that M is a left invariant mean, so that M of 1 equal to the norm of M equal to 1, and also this mean must be left invariant. So for any phi in L infinity and for any G in G, we have this equality. This is left invariant mean on L infinity. But we know that CB of G is a subset of L infinity. And our functional M is a functional on L infinity. M is a linear and bounded function on L infinity. So we can consider the restriction of this function on CB of G. The restriction of function on this subset. So this is a function for us CB of G to C. And if we denoted this by M0, for example, M0 is a bounded and linear function from CB of G to C. So that this is a function in the dual of this space. And trivially, we have these equalities for any element of CB of G. When we have this for any phi in L infinity, this holds for any phi in CB of G. Because any element of CB of G is an element of L infinity, and this holds for any element of L infinity of G. Okay? So that by this linear bounded function from L infinity to C, we found a bounded linear function on CB of G. And this is a mean and this is the left invariant mean. We have this equality. This norm equal to 1. And so M0 is a left invariant mean on this space. And you prove the part 2. There is a left invariant mean on CB of G. This left invariant mean is the restriction of M to CB of G. The restriction of M to CB of G. Note that if M belongs to the dual of X and Y is a dense subset of X, then the operator norm of the restriction of M to Y equal to the norm of M, and this restriction is the function from Y to C. This is the restriction of M to Y. Now 2 plus 3 is similar because this is a subset of CB of G. LUC of G is a subset of CB of G. Now we prove 3 implies 4. Let M from LUC of G to C be a left invariant mean. Left invariant mean on LUC of G. We must form a left invariant mean on RUC of G. Okay. We define M tilde, for example, from RUC of G to C by this function rules. M tilde of phi star f equal to m of f star phi for any phi in L infinity and f in L1. We recall that RUC equal to the set of all functions by this form: phi star f for one phi in infinity and f belong to L1. And we know that LUC is the set of all functions by this form: f star phi such that f belong to L1 and phi belong to L infinity. Please note that RUC of G equal to L infinity of G star L1 of G LUC of G equal to L1 star L infinity L infinity of G. Okay, so that any element of RUC of G have this for one and f star G is an element of LUC of G, so that M can be act on this function on LUC of G. So by this function from LUC of G, we construct a function from RUC to G. Then for any G in G, M tilde of phi star f of delta G equal to M tilde of delta G star phi star f, and this is equal to M of f star this by this function rules. And this is equal to M of f star delta G star phi equal to M of delta G star f star G. This holds obviously, and this is equal to M of f star G because M is a left invariant mean. And 4 to 5 is similar. 4 to 5 is similar because this is a subset of this. So we must prove only 5 to 1. And this holds let me review its proof from your book. Five to 1. Let M be a left invariant mean on UC of G by lemma 118. M is also topologically left invariant. We see that any left invariant mean on UC of G is a topologically left invariant mean on UC of G. Now let this net be a bounded approximate identity for L1. We know that L1 have a bounded approximate identity, and this net belongs to P of G, and choose an ultra filter U on the index set E alpha, the index set of this net, okay, that dominate the order field. Define M tilde from L infinity to C by this function rule. Phi maps to this limit. Please note that E alpha star phi star E alpha is an element of UC of G. You know this because by our appendix, let me recall this again for you. Okay, this is the approximate identity for L1. All of these functions are positive and the norm of this equal to 1, so that all of this must belong to P of G. Okay, and also we have these very nice equalities. This is the definition of left uniformly continuous, right uniformly continuous, and uniformly continuous function on G. But we have these equalities, okay? LUC of G equal to the set of all F star phi such that F belongs to L1 and phi belongs to L infinity, or UC of G equal to this set and UC, so that UC of G equal to F infinity star L1. Okay, so if we consider this, okay, okay, if we consider this E alpha star phi star E alpha is an element of UC of G, so that we can define this because M is a functional on UC of G and this is an element of UC of G. By proposition 8 to 5, this is well defined, that I recall this for you. It is easily seen that M tilde is a mean. Please check this. It is very trivial that the norm of this M equal to 1 and M of 1 equal to 1. And for any phi in infinity and F in P of G, we have these equalities. M tilde of F star phi equal to this limit, equal to this limit, and finally M tilde. This is M tilde of F by our definition. Okay, by our definition, M tilde of V equal to this. So M tilde is a topologically left invariant mean, and by lemma 117 M tilde is a left invariant, and we prove the implication 5 to 1. Okay, It is enough for this session, dear students. We can continue in the next session. Dear students, do you have any questions? Okay. We will continue in the next session, inshallah.